Go.
Chapter 13.8 talks about H1 NMR, proton spectroscopy, and equivalence. What does the H1 NMR tell us? It tells us the number of hydrogen atoms in a molecule, in a compound, as well as the number about the neighboring hydrogen. First, we have to decide how we determine the equivalency of hydrogen on a molecule. To do this, you would substitute an X group with hydrogen atom. There's four possible results. There's heterotopic, which is also known as unrelated. So if you take C1 and C2, C3, the hydrogen atoms, there's CH3 and CH2. So HA, when substituted with X, would yield a different absorption than HB if it was substituted with X. Therefore, they're chemically unrelated and yield different absorptions on the NMR. The next one is homotopic. That would be if you were going to substitute either HB or HB on the C3 carbon. In this example, the X, it would not matter because they're chemically identical and have the same absorption in the NMR spectrum. The next one is an anisotopic, which would be if there was chirality in the molecule. So say at C3, we had chirality. Therefore, they're prochiral. And when you substitute an X onto either of them, they would yield a chiral center, making enantiomers. Therefore, they're not electronically equivalent, but they still will have the same absorption on an NMR spectrum. The last thing is diastereotopic. So we'll take R2-butanol, which means it already has chirality in it. It's actually OH. So when you substitute the X onto either this or this, you create a second chiral center, making the final molecule a diastereomer. So now let's do some examples of some molecules. We have to choose whether they're unrelated, heterotopic, enantiotopic, or diastereotopic. Alright, so A.
Isn't the heterotopic the same as unrelated? Are you looking at homotopic?
Right. Thank you very much. Homotopic. Alright. So when looking at these hydrogens, we see that they're bonded to two different things. This is a methyl group, and this is a carbon containing a double bond L. So they're two different things. And so, if you replace it with an X, it will cause it to be chiral, therefore yielding an enantiotopic hydrogen. Let's try this. Next one is these hydrogens. We're looking at these ones right here. Alright, so right here, this is already a chiral center. This is not a chiral center. But if you replace this with an X, it creates two chiral centers because the bonds next to them will be different. So it's diastereotopic. And the last one we have two hydrogens in the front position, so when they're in the same spot. Therefore, if you replaced an X with either of them, they would yield the same thing. They'd be homotopic. And they would have the same absorption. Alright. Lastly, we're going to try to figure out the number of unrelated hydrogens on a molecule. So we'll just try a basic one. In this molecule, these will all be the same because they're all bonded to the same thing, and they couldn't create a chiral center because they're all the same. It's a CH3. Now this is not the same as this one because there's a bromine on it. Therefore, there are two unequivalent hydrogens. Now what about this one? Now we draw in all the hydrogens, so we would put H, two on this, one here, two here. So this molecule contains symmetry because of the double bond. So therefore, these hydrogens would be labeled A as well as these. And these hydrogens would be labeled B as well as these. And this would be C. So in this one, there's 1, 2, 3 non-unequivalent hydrogens. That's it. You just have to realize that when there's chiral centers, that they will make it so you have different absorptions